Time does not move at a constant speed. However, our clocks do. In the attempts to make our consistent timepieces synchronized with the dynamics of time, some strange events have transpired. Let's level the playing field here first. The Earth is split up into meridians. Basically, they're like orange slices from a whole orange, except way more. You are on a meridian as of this moment, and your meridian is just the line that connects you to the North and South Pole. Your perception of noon is just when your meridian is facing the sun directly, causing all your shadows to point to a specific pole. However, sometimes shadows do not point anywhere. This is because the sun would be directly overhead. This point is called the subsolar point, and it is always somewhere on Earth, mostly in the ocean, but sometimes on land too. Anyways, back to noon. When your shadow is pointing to either pole, you are experiencing local apparent solar noon. However, this local apparent solar noon technically lasts about a second or so, because the Earth is constantly rotating, so the sun will be in the highest place for a very short time. This results in our first problem. Clocks for you and your friend, who lives on the other side of the city, would not agree if our clocks were based on local apparent solar noon. One of you would experience it slightly after the other has. The not-so-perfect concept of time zones comes into play here, unifying time on a regional scale whilst dividing it on a global scale. Because of this, you and your friend see the same time now. However, countries are not simple boxes that are perfectly aligned, but tracts of land with wiggly borders. So, for time zones to truly unify regional time, it had to be wiggly too. Like, very wiggly. So much so that for some meridians, just traveling north or south can change your time zone. Despite all its flaws, time zones are the best we did in terms of shadow-based time. However, that is just the tip of the iceberg. Moving on to the next unit of measuring time. What is a day? Surely it must be the time it takes for Earth to turn 360 degrees, right? No. Firstly, measuring the time that Earth takes to rotate 360 degrees is a challenge on its own. There's no cosmic graph paper to measure a rotation of 360 degrees on. The next best alternative is to measure using the furthest objects possible, such as a galaxy, tracking our rotation relative to it. The reason this works is that distant galaxies do not move much, like the landscape when you're driving in a car. With this method, the length of a sidereal day, or a day pertaining to the stars, is 23 hours, 56 minutes, and 3.93 seconds. The 24 hours you are accustomed to is the result of rounding this value off, right? Sure, the difference is a mere 4 minutes, but over time, those 4 minutes will add up and eventually throw off our calendar. To reiterate, our calendar is not based on a sidereal day. There is another reason why our calendars are not based around vague points of light. There is a far closer star that plays a huge role in what we call a day. The Sun. The Sun does not change Earth's rotation, at least in short term. It is still 23.9 hours. However, what does change is Earth's position around the Sun. After one sidereal day, Earth would have moved a bit along its orbit, and because the Earth orbits in the same direction that it rotates in, some extra rotation is necessary for the same meridian to point to the Sun. By the way, that extra time is not 4 minutes. This longer day is called a solar day, and its duration does vary quite a bit. This is because the duration needed for Earth to rotate that extra bit to point the same meridian at the Sun depends on the position of Earth in its orbit. Earth's orbit, or any orbit in the solar system for that matter, is not a perfect circle, but an ellipse. This ellipse is why, on paper, Summers in the southern hemisphere are just a little warmer than the summers in the northern hemisphere. This difference in distance from the sun means that in July, the Earth does not need a lot of extra rotation to complete a solar day, whereas in January, Earth would need to rotate quite a bit more to complete a solar day. Despite this, our species decided to take the average of all these solar day lengths, 24.000006 hours, as the day that our phone clocks and watches use. Why did we do this instead of just playing along with the different day lengths? Consistency. It is not practical for any of us to constantly worry about when the day precisely ends, so we prefer taking the mean. Proof that we use averages are evident and can easily be seen if looked for. This is a solar graph. It is a graph that tracks the path that the sun takes in the sky over a period of what we call a year, which I'll come to in a moment. Now, if our clocks adjusted time to match the dynamic solar day, then if you took a picture of the sun at noon every single day, the result would be a straight line of suns. But we know that is not true. If you took a picture of the sun every day at noon, you would get an H-shaped figure of suns. This H-shaped diagram that you would have acquired would be called an analemma. It is not straight because at some points in the year, our clocks fall behind the solar day, only to overtake it later in the year. It's an endless race. Despite this, long ago, our species was determined. They were undeterred by this irregularity. They formulated the equation of time, which reconciled our clocks with Earth. Other than looking like your heartbeat when you cannot find your phone, this graph was used in conjunction with a clock to compute the actual real time that would be seen on a sundial. This was popular for a while. We had equation clocks that did all the heavy lifting for us, but at one point, it was too much. The inconsistencies were far too great for us to adapt to in daily life. This resulted in humanity switching to the 24-hour day, a decision that still stands. So far, we've seen the issues with the hour and the day. The second is a story for a later video, and the week is just 7 solar days. Now we move on to the year. Let me ask you a question. Is 2200 a leap year? What about 2300 or 2400? Truth is, although all these years are divisible by 4, only one of them is a leap year, 2400. Our year is mainly governed by seasons. In January, you're either building snowmen or sandcastles. The time between two instances of a specific season occurring is called a tropical year, or a solar year. This is the best definition of the year that we have, because it measures every season exactly, so a tropical year is always perfectly in sync with the seasons. Although a tropical year fits perfectly with the seasons, because it's built around them, it does not fit perfectly with our solar days. Aha, you say, it's 365.25. That's why we have leap years. And you would be correct, mostly. To avoid the calendar offsetting itself rapidly, we do add an extra day to every year that is divisible by 4. Again, mostly. The trend of adding a day every 4 years was introduced in the Julian calendar. This calendar was used for over a millennium. The problems that this calendar caused are mainly because of how long it was used for. A tropical year, most recently, was 365 days, 5 hours, 48 minutes, 45 seconds, and 138 milliseconds long, to be precise. The truth, though, is that the length of the tropical year fluctuates, just like the length of the solar day, because of long-term changes in space that are barely noticeable. However, Assuming our value of 365.2421891, the Julian calendar overcompensated, causing it to drift off by about 10 days by the year 1582. It is impressive that it took 1.5 millennia to drift 10 days, but we could do better. Festivals were now up to mandating our clocks to be corrected. The fix to the Julian calendar was that every year divisible by 4 was a leap year, unless it was divisible by 100, unless it was also evenly divisible by 400. This is how 2100, 2200, and 2300 are not leap years, but 2000 and 2400 are. Pope Gregory XIII introduced this on October 4, 1582, and this new calendar was now called the Gregorian calendar, aka the calendar that we use today. Since the 10-day drift was still there, he also declared that the next day was not October 5, but October 15. However, it took some other countries a while to adapt, which is why the UK has a shorter September in 1752 by 11 days, because by 1752 the Julian calendar drifted off even further. Fun fact, before the Gregorian calendar, the year began with March, which is why part of February was always sacrificed. The switch to the Gregorian calendar realigned the calendars with significant improvements in precision, but obviously it is not perfect. The Gregorian calendar will drift off by 1 day every 3,216 years, which is an exponential improvement over the puny 128 years that the Julian calendar needed. But let's hold on for a minute. Theoretically, what is the perfect calendar? Forgetting mortal constraints and impracticality, how can we adjust our year to be as perfectly in sync to Earth's motion as possible? Let's see. So far, the rules in place are every 4 years an extra day is added to the calendar, but if the day is divisible by 100, then it is not a leap year, unless it is also divisible by 400, in which case it would be a leap year. Here are the extra additions we will make. If a year ends in 2800 or 5600 or 8400, then it is not a leap year. With this extra caveat in place, calendars would need 91,743 years to drift off by 1 day. But we can do even better. Instead of correcting the Gregorian calendar, what if we try correcting the Julian calendar? Sure, the Julian calendar does drift off faster, but its drift is an almost exact 128 years, 128.026. It is so close that skipping a leap year every 128 years solves the issue better than the Gregorian fix that we applied. How would we know if a year is divisible by 128? Remember, we are not considering impracticality. So all we must do is write the year number in binary. Now in binary, if the last 2 digits are 0, it is divisible by 4. But if the last 7 digits are 0, then it is divisible by 128. Last 2 digits 0, leap year. Last 7 digits 0, nope, not a leap year. It's simple really. This calendar drifts off by 1 day every 625,000 years compared to the current 3,216 years. But wait, we can do even better. Now if we also skip a leap year every 625,024 years, the calendar deviates 1 day every 53.5 trillion years. That is far more than the current age of the universe, which is, relatively and roughly, a mere 13 billion years old. Although that calendar sounds easy to implement, why is it impractical? Everything around us, from spacecraft to the moon to other planets, constantly play tug-of-war that minutely changes Earth's movement. This movement will be quite significant by 50 trillion years, if we exist at all, so this calendar will be obsolete and new methods will be needed to reconcile the clocks to the motion of whatever planet our species will be exploiting at that time. But then you might ask, what is the point of all this trouble, all this pain, all this effort of trying to precisely slice up Earth's motion and name it? Why don't we just pull back our camp chairs and enjoy it? There are valid reasons to want to reconcile Earth's motion and our perception of time. Starting with agriculture, farmers need to know which months are the best for planting crop A. If we didn't care about leap years at all, within a farmer's lifetime, the best time to plant crop A could go from being late April to early June. Every 50 years, libraries worth of books would need to be rewritten to readapt to Earth's seasons. Not caring about the length of a year could have serious implications on religious prospects too. Festivals could go months off from the time of their origin, and historic days would drift off too. The implications are clearly way beyond what we think of. Hence, it is vital to keep our clocks in check. Finally, the trouble with the hour, day, and year have been solved, mostly.